Okay.
Okay. Yeah. Good afternoon, everybody. So glad to be back again to talk about research work from my team. So today I will focus on one particular topic about universal natural language understanding. Okay. So before I get started, I want to ask everybody a quick question. You can answer the question through chat. So can you tell me, how many languages are there in the world? Can everybody take a guess? You can just type in the chat. I think we can. Okay, so we have a guess, 2,000, 10,000, over 1,000. Okay, in terms of granularity, no, not 100,000. Luckily, yeah. So I think the one guessed 10,000 is the closest one. So we have about a little over 7,000 known languages, with 23 of them most spoken by 4.1 billion people. So you can see the distribution of language and by the number of speakers. But if you think about data, like language resources, right, in terms of different language, it definitely very much biased towards English. Right now, the conventional way of enable different capability for different languages is like taking one language, build a pipeline for that language, and then empower the corresponding application, building one for English, build another one for German, for Chinese, and so on. Clearly, this is going to require a lot of efforts to expand any capability across different languages. So instead, we are proposing that rather than building one language at a time in terms of the natural language understanding component, we can build one that is universal across different languages. And then when we build applications on top of this, the universal representation, then we get the cross-lingual support for free. So what are the challenges to enable this? So on the high level, there's three categories of challenges. One is meaning representation. When we talk about we want to build a cross-lingual natural language understanding, we need to represent those natural language in certain meaning representation. But as I will show you in a moment, right now there are different meaning representation for different languages, and in fact, even for the same English, like English, same language like English, we have different meaning representation. So the first challenge is how do we come up with a unified meaning representation? The second challenge is training data. Assuming we decide a particular meaning representation to go, then in order to build models to be able to produce those kind of meaning representation, we need to be able to obtain training data labeled in that meaning representation of sufficient quantity. Then we can train a machine learning model to actually produce a prediction. So that's a second challenge, because obtaining high quality labeled data for any task is difficult, is especially difficult for natural language understanding. Then the third part is there are a lot of special challenges related to natural language understanding, including low frequency exception, which I will talk in more details later on, as well as how do we build models on top of it. To build it one task at a time is very labor intensive and time consuming. How can we scale the building models on top of natural language understanding the meaning representations that we talk about? So that's the general outline for this talk. I will go into the unified meaning representation first. So I think for some of the people in the classroom, probably you already heard about semantic role labeling as a task, because I think some of you did some project with my team, and one of the projects related to semantic role labeling. But for those of you who are not familiar with the task, on the high level, it's actually very simple. What it does is to provide an out-of-box understanding of an individual sentence and understand who did what, to whom, when, where, and how. So for example, for this particular sentence, we can understand, okay, there is an action order. We have John perform the action, and the order, what is ordered is a dozen dandelion, and then the person received the gift is Mary, and the purchase was made in a little flower shop, and the action is done in a hastily manner. So if we think about meaning representation, right, we need to think about what is actually carried across different languages very well. If you think about syntax, definitely across different languages, the syntax looks very, very different. But the shallow semantic label remains stable. So we have some example here, even within the same language, right? The same semantics, when expressed in different way, if you look at, for example, this three sentence and you send it to a dependency parser, right, or constituency parser, you're gonna get a very different parse tree. But if you run this through shallow semantic labeling, you're gonna see all this predicate and argument, they remain stable, right? Because the semantic is the same regardless of how you say them. In addition, one thing I want to point out is for every predicate, there is a sense number. Because as we know, right, in most languages, one single word can mean a few different things depending on context. And the sense will tell you within this context, what's the specific meaning of this particular predicate. Like, for example, break here means physically break something versus break a news, right, make something known. So it's clear that if we want to build anything cross-lingual, we want to go with meaning representation, go with something like semantic role labeling, right? And then we can look at what are the resources available. So for English, we have FrameNet, we have Proper Bank. For other languages, we have Chinese Proper Bank, Hindu Proper Bank, and so on. On the surface, it looks like there are two problems, right? One is, first of all, we talk about we have 7,000 languages, right? And then even the most spoken ones are 23 of them. If you look at what are available, the number is very small compared to the languages we actually need to support. The second part is when we look at those data sets more carefully, even though they have the same name, right, like Proper Bank or FrameNet, if you look deep in details, the same, the predicate of the same meaning across different languages actually have different frames. So for example, we have order here in English, and then we have 定购 means order, the same sense in Chinese, but the actual frame is different. So as a result, even though we have different proper bank for a few different languages, when we train a model over different proper bank, the prediction will be different. So we cannot really benefit from those different annotation across different languages.
Hi, Yunyao, I think your audio and video froze.
My audio froze?
Okay, now you're back.
Okay, maybe my internet is not very stable. Okay, let me close this one first. Okay, it is now better?
Yes.
Okay, yeah. Okay, so what do you mean by having the same semantic label across different languages? So here is an example. So here I have three sentences in three different languages. When we have cross-lingual meaning representation, they all turn into the same predicate argument structure, where the predicate is buy 01, and the buyer is Facebook, and transport is WhatsApp. So you can see, even though these are from different languages and constructed a different way, they all turn into identical meaning representation. And I will show you in a few slides, later on how this can be leveraged to support cross-lingual natural language processing. So now we have basically borrowed the idea similar to universal parallel speech tagging, universal dependency parsing. We want to borrow the annotation from English label to other languages in a universal way. So with that given, the question is, how do we build it, right? So we want to have shared frame set as much as possible and also be able to create a data set with minimal efforts. So how people create proper bank today. So if we look at the few proper bank we mentioned earlier, right, what happens is, first of all, the linguists train annotators who are also typically trained linguists to go through the annotation guideline. This may take a few months, and then the actual annotation can take a couple of years or even more. And this process is repeated for each language. So often, basically, people get an entire dissertation by creating one such data set. Obviously, it's not very scalable, right? And not to mention that often we need more data than what is provided from those kind of proper bank. So the idea we had a few years ago was that we can leverage parallel corpora. So the data set, like, for example, TV subtitle, where we have one sentence in English and then another sentence with identical meaning in another language. So we can project the annotation from English to another language through annotation projection. So this way, unless we have parallel corpora, we can easily create annotated data for any targeted language. And we can get a large amount of them because this can be done completely automatically, right? However, it's not the whole thing, because projection may not always be possible. So as I shown here as an example, right, the projection actually created an error. So for example, hold is mapping to be those here. The reason is there's translation shift. When people translate from one sentence to another in different languages, they may not do very literal translation. They may take the semantic meaning and then rewrite it into a more natural way or an alternative way in the different language. So then in those cases, the projection will cause errors. The second part is also for source language like English, right? The model itself will not work perfectly. So any errors that we have on the English SRL side will be carried out and resulting errors in the other language. So to overcome those issues, we come up with a two-step process. The first step is to say, okay, we have large amount of data obtained through automatic projection. We can design filters to detect potential errors and just remove those sentences contains errors altogether. So unless we have sufficient parallel corpora, we can still have large amount of data left after the filtering step. So filtering step really focus on precision at the sacrifice of recall. Then we can use those small amount of data to train a model to do prediction, which will then add additional label back into the projected data. And then we can basically increase recall while maintaining precision. So with this approach, we have generated the 7 universal proper bank. So you can see the results here. The quality is pretty high. Overall, the only one that the quality is relatively on the lower side is Hindi. The reason is the size of Hindi is small. So if we look at the number of sentences we have in the corpus, right, all the other ones are at tens or hundreds or thousands of sentences, while for Hindi is only less than 2,000 sentences. So basically, the larger data set we have, the higher quality we can obtain through this particular method, because then we can obtain large amount of data that are projected through the target language at a high precision. So this is a data set we released a few years ago, and now we're actually working on a newer version, which hopefully will come in Q1 2022. So after we did that particular work, we're also looking into how can we incorporate language information or language expertise in the whole process, because what I just described, right, completely automated. So we want to look into can human help, but without spending years of efforts to look at the individual instances, and that is a very time-consuming process, as we have described. So the first thing we have done is really look into when we project the annotation from one language to another. First of all, certain mapping may not be valid. So those kind of mapping can be identified very easily by human, right? Because even though the hundreds of thousands of sentences, the actual frame mapping at a scale of a couple of thousand. So this scale is completely containable through manual examination. So we designed that process to enable language experts to inspect all these frame errors and also be able to merge the frames. So in the end, we significantly improve the quality of the automatically generated data by removing, wrongly projected mapped frame and then merge those redundant ones. So in the end, we reduce the number of frames and reduce the number of sentences, but significantly improve the quality of the data. So this process for each language take about 1 to 2 weeks. The second thing we also did was that for the initial annotation projection to work, we assume there is the dependency parser available, and we use the dependency structure to help with annotation projection. However, not every sentence, not every language actually have dependency parsing or lemmatization, etc. available. So we also look into those low resources languages and see whether just by sentence alignment we can produce reasonable data set. So here we can see, right, the initial projected data here, then we also have a crowd in the loop approach for someone with language expertise to help with curate the data further. However, if we can see here, it's kind of mixed success. The reason is that the task itself is challenging. So for the cases where machine make a mistake, human also tend to make a mistake. So this particular paper basically show, okay, it's possible to actually produce reasonable data set for low resource language, but at the same time, it's not so straightforward to do crowdsourcing for this kind of task. Then we spend the next few years really looking into how can we crowdsource this particular task? Is there any way we can make it possible? So we first look into why the human make mistake. We then find, okay, for certain tasks that machine make mistake, human also tend to make mistake. In fact, what we found is if you just give the task to the user to say, okay, this is machine predicted results, is it correct or yes or no? It has two issues. One is the human always biased towards machine because machine quality is actually pretty reasonable. The second part is the certain task when the machine is not sure, human is also unsure. And our experience is that even when five cross worker agree, they can all be wrong. So therefore, if you just use the traditional approach of splitting a larger task into smaller one and then give to individual crowdsourced worker, in this case, it will not work. So we tried a few different approaches. The first approach is, let's just admit that it is impossible to let crowd to do the entire task. Then our goal is to identify a sub portion that are doable by the crowd and leave the rest to the expert. So in order to do that, we basically train an initial classifier and compare the crowdsourced worker performance with expert and then let the classifier learn to predict how difficult a particular task is to a crowdsourced worker. So we use SVM classifier. We would have sentence level feature, task level feature, and this allows us to be able to effectively identify tasks that are challenging to the crowd. So in that case, we basically give the challenging task to the expert. So what we have found is, compare with the machine created data, we improve the F1 measure by 9%, and then we reduce the effort required by expert by about 2/3. So this is pretty successful in terms of reducing effort required from expert point of view. Then later on, last year, we actually have one more paper where we're looking to, because in order to learn the classifier, it also takes some effort from the expert, right? And also reducing 2/3 is still not sufficiently significant. Like, we want to reduce even further. We want to look into, can we come up with a more intelligent way to reduce the efforts further? So what we did, we come up with a process where we first give the task to the crowd and basically allow the crowd to filter down the options from often 20 different options to only 3. Then the crowd only select from those 3. If they still have difficulty to decide among the 3 which one to pick, then that task go to expert. So through this, sounds very simple, but a very effective process, we improve the quantity by 10 percentage points and reduce expert efforts by 87.3 percentage points. So this is a significant improvement compared to even what we have done a few years back with crowd in the loop. So this particular experiences really show to us that when we do crowdsourcing, it's really important to do quality control, understand whether the crowd really produce high quality data as expected. If not, look into why, and then design a process to address all these challenges. So I don't have time to go into details, but I really encourage you to look into this paper if you have any plan to do crowdsourcing in the future, because it's very tricky. Like, often in these days, we have the tendency to say crowdsourced worker created data is a gold data, but as you can see from what I'm showing here, it's far from the case, right? So we really have to be very careful when we say something is manually curated by expert is very different from curated by crowd, especially without any quality control. The second thing I want to talk about, again, related to training data is, remember I talked about earlier, right? We have data set from different languages already. So one question we want to examine is, can we leverage some of this data? Is there a way to do that? So as I showed earlier, right, from different languages, we want to come up with the same cross-lingual representation. But the challenge is that in the current setting, of the proper bank for every different language, the annotation is actually done differently. So we want to leverage something called a cross-lingual transfer. So we want to transfer knowledge and resource from high-rich resource language to low-resource language. So let me describe how do we do that. So the main idea is combine all the training data together using multilingual word embedding and train a common encoder model to enable parameter sharing. But as I described earlier, right, the challenge is different languages, the proper bank are labeled differently. So for example, we can see here we have 3 languages, right? And if you look at the labeling here, the labeling set is different. Like in one, we have in Chinese, we have temp. In another, we have am temp. And then in here, we have a different set. So, but however, we do observe that even though the argument label are not exactly the same, they do tend to share some commonality across different languages. So our intuition is if we can identify those commonality, it is possible to actually explore the commonality better in a shared vector space. So for example, here we have two different languages, right? One is the English, another is the German, I believe. So if you look at the frames, even though the exact label is not the same, at least we can see there are some, we have A0 that is the same, and the A1 is the same also. Then we have AM that is also same. So even though they're not identical, there are still sufficient amount of commonality. So the way we can explore those is first doing pair matching. We identify argument with similar semantic meaning across languages, and then doing argument regularization and represent them close to each other in the feature space. So the regularizer is applied as a parameter of the last layer of the model. And this approach has a few different benefits. One is it is dependent on the base model. We have no dependency of the base model because it is added at the last layer, right? And also it's independent of language. You know, none of the method have any dependency related to a particular language. And also it requires no parallel data. So we can leverage whatever data set available out there. And if we look at the results, by using this approach, what we call the CLAIR, we obtain average, best performance across all the languages and increase the average performance by close to 5 percentage points. And also from 3 out of 5 non-English languages, we actually works better than those are trained individually for those independent data set, individual data set. So this really shows that this method is effective of porting knowledge from high resource language to other languages, even though the annotations labels may be different. Okay, so now we'll talk about, how do we overcome the challenge of training data. We're going to talk a little bit more about how do we build models.
Yunyao, Can we maybe pause just a second to see if there are any questions?
Yeah.
Any questions either from in person or online? If so, you can also ask in the chat box. Okay, looks like there are no questions, so okay, go ahead.
Okay, no problem. Okay, so so now next I will talk about the building models. This number is slightly outdated, but the overall message is the same, that the current state-of-the-art model for dependency parser, if we look at F1 measure, it's a few percentage points higher than the one for semantic role labeling. So you may want to ask, what makes semantic role labeling so difficult? So there are a few different reasons. One of the biggest reasons is that the class labels for the different predicates are not uniform. So instead, it has a heavy tail distribution of class label. So if we look at the training data like proper bank, there are a lot of common frames, ones appear thousands of times, and then the ones that appear very few times. In fact, almost half of all frames seen fewer than 3 times in training data. There are a lot of low frequency exceptions make it difficult to generalize in model, right? So let me give you an example. So for instance, if we look at those sentences, right, where if we look at the passive, those are all in passive voice, right? If we look at this passive subject in those sentences, in the first one, it's labeled as A1. The second one is labeled as A1 as well. However, if we look at the third sentence, we have to look at the frame to decide whether the subject creditor should be A1 or A0 or, or A2. So do you want to take a guess what it is should it be? Should it be A1 or A2? You can type in the chat. Okay, so we have some guess here. Yes, it should be A2. However, if we look at the numbers, right, within the data set, regardless of which frame, any passive subject are labeled as like 86% of passive subjects are labeled as A1, which means if we just blindly forget about a particular predicate, if we just blindly label every passive subject as A1, we're going to be correct 86% of the time. But the challenge is what to do with those ones that are different, right? For example, for tail, when tail appear in a sentence, its passive subject, 87% of the passive subject should be labeled as A2 because of the particular frame we look at. So which basically means that when we generalize in the model to say passive subject should be A1, we have to incorporate a lot of exceptions for different kind of frames, right? So we come up with a method. This is something we have done a few years ago, but it looks very simple, but it works surprisingly well. So this is very similar to how we human generalize, right? If you think about, you learn about certain knowledge, right? And then you have a new thing comes in, you always compare to say, how similar this particular sentence is the one I know before. So the idea here is also similar, like basically find a way to capture the training data. So then at the prediction time, we can derive that for this unknown sentence, which ones from the training data is most similar to the one we have seen before. The main challenge is to define similarity, and then how do we order those features? So for example, one of the features can be find me all the sentence contains predicate tail 01, find its passive subject where the passive subject has a head or creditor. If so, this is the closest one. So you find as many of those as possible. And then you back up to say, okay, find me any sentence contains tail 01 with none as passive subject. So you kind of go find more and more sentences are similar with the unknown sentence. And once you obtain enough number of sentences, you can do prediction. You can say, find me all these sentences that close to the unknown one within distance of 3, for example. And then you can do a majority vote. You can say, okay, let's look at all the number here, right? So based on distance within 3, we can decide this particular label should be A2. So you guys are correct. It should be A2, and this is how this particular algorithm perform this particular task. So this may sound like a simple algorithm, but it works actually quite well. So again, this number is the state of the art a few years ago, right? But still you can see compared to more complex model like LSTM, we actually perform better for both in domain and significantly better for out of domain because this generalized pretty well. So it has very small neighborhood, right? We don't need to look into many different examples. Instead, we can just look at neighbors within distance of 3, and it's very fast. So this is still something we use in production today, even though we have state-of-the-art results already that combine deep learning plus instance-based learning. We still use this particular model because it's really fast and it works pretty well. Of course, we still continue the research here. We want to look into whether we can get something works even better, both in terms of the quality as well as reasonable runtime. So this is something I think many of you work in practice know, right? It's not just about quality. Runtime performance also quite important. Okay, so this is one line, and then I have talked about, the reason of building this cross-lingual representation is so that we can enable advanced natural language processing applications built for easy multilingual support. So we created this cross-lingual representation, and one way is to support cross-lingual extraction. So here, for example, I can just say, find me all the sentence, right, condense by, and return me the buyer, and since they bought, then I magically get all the answers from all the different sentences. So you can look at some of a paper we have published earlier and also a video demo here. But now I'm going to show you a system we built for production. So this is a system we built for production for contract understanding. What it does is when we load the data set consists of a contract, we want to help legal professionals better understand the contract. How do we help them? So when we load the contract, we first identify individual sentences as elements, and then we give those elements some label. And then the legal professionals can now zoom in to say, okay, with the contract, now I want to focus on pricing and taxes. So they don't need to look at the entire document. Instead, they can go in this particular document and just look into the ones that is labeled for that particular category. They can also provide user feedback in case there are some mistakes they identified. So how do we create this particular model? On the high level, basically, we first do element identification. For simplicity, think of it sentence identification. But in reality, not so simple. If you have ever read a legal contract, you would know a legal contract typically contains at least quite a number of pages, sometimes hundreds of pages, right? And then the element can be anywhere. It can be nested, bulleted list, how to identify the boundary of the sentence is already quite a challenge. But assuming that task is done, we identify all the elements. Then the second part is we turn the meaning representation into something like this, so that from the original unstructured data, we turn into a semi-structured representation where we can see there is an action of purchase, there is the A0 of the action and A1, and also how the action was performed, as well as the tense of the action. Then what we have is the legal professionals actually work with our NLP engineers to code the domain knowledge to capture what is considered as a different kind of clause in contract. So for example, one of the logical expression may be the following: identify all the business transaction predicate, identify those that the tense is future and the polarity is positive, and label it as obligation and identify argument 0 as a party. So what is this return is, this is an obligation clause, the original element for purchaser. So this is what we get from this particular model. So you may wondering, I don't have a slide here, but I can describe at a high level. You may wondering why we build this approach. Why don't we just get labeled data and then train a black box model? So I have two answers. One is we did. We actually trained that black box model. But the reason we go with this current approach is that for enterprise NLP services, right, like this one, it's really difficult to think about a representative data set, because for a machine learning model to work well, you need something representative. But if you think about legal contract, it is simply impossible for any company to obtain all the, even a small subset of all the contract out there. So therefore, what we have found is when we use a black box model, the model works well within the domain. But at the moment we go out of domain, the quality drops very significantly. So this is why, especially when we don't have large amount of data to start with, this is why we started with this transparent model design. However, we do realize, to manually create this kind of model is very time consuming and expensive. So this is where we, our research also come out with a plan to say, if there is enough amount of label data available, can we do better, right? We still want to benefit from this transparent design, but we really want to reduce the manual efforts. So this is the work we have done. We have been doing, for the past couple of years. So we take label data, we apply deep learning, we learn the linguistic expression like what we have seen before. Then we have a human loop tuning to allow the NLP engineers to interact with the tuning to make further modification. So this is what the tool looks like right now. We're actually working on a more improved version of this. So a few things we provide, right? One is for individual rules, we provide the performance metrics so that the user can say, I only care about high quality, for example, high precision rules rather than high recall rules. So we allow them to select, filter those rules based on those criteria. Then we also allow them to say, okay, for each particular rule, what are the corresponding matches for them, right? Because if you just look at it itself, it's difficult to know whether it's correct or not. So we provided those examples to allow the user to be able to make decisions. And we also allow the user to play with the rules to say, okay, this sounds like a reasonable rule, like look at the section title, look at the voice, but maybe we don't need to worry about tense. So the user can decide to drop the tense, and you can see when the user drops the tense, precision remains the same, recall increase, and the overall F1 measure increase. So this really allows the user to be able to play with what created by the machine and inject additional domain knowledge that otherwise we cannot learn from the data alone. And then based on our user study, this is a very effective approach. The user, with the help of this tool, is able to create a model within half an hour that is at least comparable, if not better than black box model. And also when we combine all this, average NLP engineer together, their models is of very comparable quality as the NLP experts. So this really demonstrates the value of having this kind of system that is not only reduce the human efforts, but it's also resulting in model of high quality. So any questions so far?
Go ahead. Yeah, you have a question in the audience.
Yeah. So how do you construct these rules? Is this a process done similarly to something like decision trees where you restrict the complexity of them so they are interpretable? Because you mentioned it's a rule neural network, so I was wondering how that works.
Yeah, well, this is we actually learn rules very similar to the linguistic expression. So I don't have a, do I have a slide here? Yeah, I don't have a slide here that actually shows how we learn those rules. But basically you can think of, we turn each layers of the deep learning neural network into corresponding predicate. And then when we learn, we can know which predicate to keep, which one to drop. And in the end, we basically end up to learn logical expression like this one.
Okay, thank you.
Yeah. Okay. So another thing we have also done is these days, right, like what I talked about earlier, the cross-lingual transfer, a popular approach of handle low resource setting is through transfer learning. So we can also combine transfer learning with what I just talked about. You can think about with small amount of label data and pre-trained language embedding, we can do transfer learning, learn a black box model. And this black box model can use to label larger amount of noisy label data that then fit into the pipeline we just described, fit into deep learning that learn rules, and the rules can be further augmented. But more importantly, those rules can ensemble with the black box model and result in a model with higher quality and better explainability. So let me show you some numbers here. Yeah, unfortunately, I don't have animation. So let's just look at one table at a time, okay? So this is something we have in production. So this is manually written rule for out-of-domain performance. So it's very important to think about. Out-of-domain performance is typically much worse than in-domain. So therefore, when you look at this result, it's actually very decent, especially consider very high precision, okay? Now, if we just apply BERT-based model plus the transfer learning, this is what we get. So F1 measure is a few percentage lower with significantly worse precision, but higher recall, right? Then when we use the black box model to label additional data and then fit into a rule learning framework, we learn rules that with high precision, lower recall, but overall higher F1 measure that is even slightly higher than the one that put in production, created manually by human. But what is even better is when we combine the black box model with the white box model by different ensemble strategy. One is to look into using product, which basically means that we favor the ones that have the same prediction, right? Basically, if we look at this tool, we keep the precision. We actually boost the precision to be even higher, and the recall drop because for a lot of the cases, you know, the rule-based model do not produce prediction. So then the recall drop, but overall F1 measure is higher, and it can explain about 90% of the cases. Another approach is to say we will always apply rule. If the rule-based approach produces no prediction, then we will use the BERT-based model as a fallback. With this one, we have very high recall, right? Not very surprising because we have a fallback model, right? But then the precision lower. The overall F1 is still higher than any of the model individually, and now we can explain about 50% of the cases. So which ensemble strategy to use really depending on the specific use case. Sometimes recall is important so that you can present as much to human as possible. In other cases, precision is more important. But the main message is that with this hybrid model, we're able to train on small amount of data, relatively small amount of data, and also be able to produce model that is of higher quality and better explainability. So this is something quite attractive for our enterprise users when they when they see a model that perform well, then they will ask for explainability. Now we're able to produce both. But of course, the rules you have seen earlier may not be viewed as completely understandable. I think people need to have some linguistic knowledge or have some training in order to understand those rules. So therefore, my team now is also working on how do we generate even simpler explanation based on those rules. So that's still ongoing work. So overall, we have been working on this direction for quite a number of years. this is very typical for our research project, where we start with maybe just a few ideas on an intern project, and then we grow in different direction, and then we create solutions, put into our product, test through our customer engagement, and then slowly growing into different direction. Like right now, for example, the multiple IBM product adopting early version of this based on English, and now we're working on adaptation for other languages. So if you are interested, you can look at some of our papers, and then as we go, we also have done some other work that we release to the public. So I hope at some point we can have some of you to visit our very beautiful Almaden lab, and IBM has a lot of lab across the world. And you can look at our website to look at some of our other papers and some other ongoing work, and then we'll also release some of the data. I think we did some very good, interesting work with students from UC Santa Cruz. So we also plan to maybe make some of those work wrap up and also release to other people. With that, that's the end of my talk. Any questions, comments?
Great. Before we do our questions, can we all please thank the speaker for a very interesting talk? Thank you very much, Yunyao. Okay, great. Let me stop there.